morning again all of you. So today we will continue on the derivation of the non-dimensional form of the Navier-Stokes equations. Particularly we are interested because as I said before, the course deals mostly with two-dimensional incompressible flows. So therefore if you I think in the last class I just gave you the non-dimensional variables which we are putting into the dimensional Navier-Stokes equations, and if you plug in, I leave that as a nice exercise. You can plug it into the steady state two-dimensional incompressible dimensional Navier-Stokes, and finally you end up getting this set of non-dimensional steady state incompressible Navier-Stokes equation for 2 dimensions. So now this is how your non-dimensional numbers come out. Okay, so all these are capital letters, which means they are non-dimensional. Okay, U, V, X, Y, capital P. Okay, so and the way that we are non-dimensionalizing is shown here. This was discussed last class. I think all of you can probably reach to this particular point. Now the following non-dimensional numbers are popping out of this particular non-dimensional set of equations. Okay, so we will discuss the non-dimensional numbers which are coming out of this. Okay, so for deriving the non-dimensional form, you can consider a flat plate boundary layer equation such as what is shown here. You are assuming a free stream velocity which is uniform, which is not varying along the x axis x direction, and you have also a temperature boundary condition which is applied to the flat plate. So this will induce a thermal boundary layer developing along with the momentum boundary layer. Okay, so the thermal boundary layer thickness is delta T, function of x. Your momentum boundary layer thickness is delta, which is also a function of x. So this is how the velocity and temperature profiles at any location will appear. Okay. So for this is a typical case where you want to finally reduce your Navier-Stokes equation to what are called as boundary layer equations. Okay. So the boundary layer flow is a approximation to the complete full solution of the Navier-Stokes equation. Okay, before we do that approximation, let us look at the non-dimensional numbers involved. Okay, so first is your Reynolds number, which is your rho infinity U infinity L by nu, where L is your characteristic length. Here we can use the characteristic length as the, for example, length of the plate. Okay, so this denotes the ratio of your inertial force to the viscous force. So if you look at the non-dimensional form of the momentum equation, so how can you use the Reynolds number to classify the flows, for example? So if your Reynolds number is very small, then this term is dominant over the other term. So you can neglect, for example, the inertia compared to the diffusion terms right here. Okay, so under the limit of small Reynolds numbers, you can have a viscous diffusion dominant flow. Okay, at very high Reynolds numbers, you can neglect the diffusion terms compared to the inertial terms. Okay, now of course you want to operate in a regime where you are not too extreme. You are not going towards a very small Reynolds number or very high Reynolds numbers. So in those practical situations, so you have both these terms which are dominant. However, the Reynolds number will also be helpful in classifying the flow regime. Okay, so if depending on the Reynolds number, you can classify for external flows, for example, laminar versus turbulent. Okay, if you take the example of a flat plate, okay, so as you start from the leading edge right here, initially it could be a laminar boundary layer, and after some certain extent, okay, your instabilities start appearing and you have a critical Reynolds number beyond which your instabilities will grow and the flow becomes turbulent, and that is classified based on the local Reynolds number. Okay, so typically your local Reynolds number, that is the critical value based upon which you classify whether the flow is laminar or turbulent. In the case of flat flow is approximately 10 to the power 5. Okay, so this is a good example how you are using the Reynolds number as a means of classifying the flows. Of course, you can also make approximations to these terms based on the Reynolds number. Very small Reynolds number you can neglect the inertial terms, extremely high Reynolds numbers you can neglect the diffusion terms. So that is one utility of Reynolds number. Now let us move to the other non-dimensional number. Okay, so what is the other number that is appearing here? Prandtl number. Okay, so your Prandtl number here is basically your mu Cp by k, which is nothing but, if you write in terms of diffusivities, momentum diffusivity by thermal diffusivity. So you can divide and multiply by rho. So this mu by rho is your nu, and k by rho Cp by k, so will give you 1 over alpha basically. So this is your momentum diffusivity. So what are the units of diffusivity? Meter square per second. Okay, okay, so now the Prandtl number is a very useful parameter, especially when you have flows with heat transfer. Okay, so Prandtl number appears in the energy equation along with the Reynolds number. So if you are looking at this this figure right here, so Prandtl number decides how far, what is the rate of growth of the velocity boundary layer with respect to the thermal boundary layer. Okay, so in this case it shows that your velocity boundary layer is growing at much higher rate than the thermal boundary layer. Okay, so your Prandtl number greater than 1 signifies that your momentum diffusivity or momentum boundary layer thickness, which is related to the diffusivity, has to be greater than your thermal boundary layer thickness. Okay, and of course vice versa, if you are looking at smaller Prandtl numbers, your momentum boundary layer thickness should be less than the thermal boundary layer thickness. Okay, so with that you can look at some approximations that you can make when you are solving the incompressible boundary layer equations. Wherever you have a very small Prandtl number approximation, for example when your momentum boundary layer thickness is much smaller, okay, so you have to make certain approximations which will simplify your flow. So these are again some kind of classifications where you can identify how the boundary layer thickness, velocity boundary layer thickness grows with respect to the thermal boundary layer thickness, and typically for gases you will have about Prandtl number close to 1. Okay, typically for liquids you will have Prandtl numbers much greater than 1. Okay, so gases have a Prandtl number approximately 1, and if you are looking at liquid metals, okay, so they fall under the category where your Prandtl number is much lower than 1. Okay, so this is the other non-dimensional number appearing in the energy equation. Now when you go to flows, suppose you have a body force here, okay, which we have not included now. Okay, you can have basically buoyancy which is driving the inertia. Okay, so that is the natural convection. So even though you don't have a forced convection, you don't have a velocity which you supply by means of an external blower or pump, you can have the natural convection happening due to the buoyancy forces, and that if you include, now instead of the Reynolds number defined for forced convection, you can define another non-dimensional number for the case of natural convection. Okay, so that is called the Grashof number. Okay, so strictly speaking I have not included here, but if you include the external buoyancy and non-dimensionalize it, you get a number which is nothing but gr by re square, the ratio of Grashof number to Reynolds number square, that is also called as Richardson number. So your Grashof number is, now since you are defining your Reynolds number as inertia force to viscous force, when you have buoyancy driven flows you do not have inertia dominance but buoyancy dominance, therefore this should be buoyancy force by viscous force. Okay, so your buoyancy force, the net buoyancy force which is acting, so it's basically your force acting downwards due to the weight of the fluid, the gravity minus the force which is acting upwards due to buoyancy, that is the net force. Okay, so that is rho minus rho infinity, you can say, into acceleration due to gravity. So if you replace the Boussinesq, if you replace the density difference, apply the Boussinesq approximation and replace it with temperature difference, so you can write it as g beta into T minus T infinity. So this is your force per unit volume. So if you want to convert it as force, so that will be multiplied by L cube divided by the viscous force which is nu square. Okay, so this is the exact way that you calculate your Grashof number once you know the temperature difference and your coefficient of, so this is your 1 by rho d rho by dt. Okay. So now we will move on to the other non-dimensional numbers, one which you are, the last one which is appearing in that particular non-dimensional form is your Eckert number. Okay, this is actually defined as the ratio of your kinetic energy of the fluid. The exact expression that comes out will be u infinity square by Cp into T wall minus T infinity. So this is nothing but, you can say the numerator is the kinetic energy of the fluid and the denominator is your thermal energy. So what it means is, if you have a high Eckert number, okay, so a portion of your kinetic energy actually gets converted into the thermal energy. Okay, so this is especially true if you have high speed flows, okay, or if you also have very high viscosity dominated flows, there you have a lot of viscous dissipation effects coming into picture, and a portion of the kinetic energy is converted into thermal energy. So even though if you maintain this wall as adiabatic, okay, so due to this viscous dissipation effects you can have a temperature profile. Okay, so the temperature profile can set in essentially because of the Eckert number which is coming into the viscous dissipation term. Alright, so this is these are some of the non-dimensional numbers. We will go ahead and define one or two more which are important for heat transfer, although they are not appearing in the governing equations, we will use them very routinely. So one is your Nusselt number. Yeah, I think this should be, so we characterize the heat transfer rate by means of a non-dimensional number, okay, so which is usually used in convection, and that is called the Nusselt number. The Nusselt number you can define based on the heat transfer coefficient, which is dimensional, multiplied by the length divided by the thermal conductivity, and where your heat transfer coefficient is defined as minus k dt by, so this is your heat flux at the wall divided by, in this case, T wall minus T infinity. Okay. Now if you use the non-dimensional temperature based on this definition right here. Can you tell me what will be the Nusselt number in terms of the non-dimensional temperature gradient? You can plug in for the non-dimensional form into the dimensional form, and then you can finally calculate your Nusselt number in terms of non-dimensional temperature gradient. It's a nice exercise, I think you can just try out. I'll give you a couple of minutes. Yes? So what should be the expression? Dou? Okay. Into L by K. Now I want to calculate the Nusselt number. Thermal conductivity cancels, and you can also write in terms of non-dimensional Y. LL cancels. So that will be minus capital Y at capital Y equal to. Okay. So this is the advantage of casting in non-dimensional form. Your expression gets much simpler. Alright. So now you understand why we define Nusselt number in this particular way. If you have a dimensional form of heat transfer coefficient which is related to the temperature gradient, your Nusselt number is exactly nothing but your non-dimensional temperature gradient. Okay. And if you look at the physical significance of Nusselt number, you can also write your Nusselt number. You can multiply the numerator and denominator by T wall minus T infinity, and you can write this as K into T wall minus T infinity by L. Okay. So this is nothing but what? What is the numerator here? This is your convective heat flux by conduction heat flux. So what does this represent? The non-dimensional number tells you what is the actual contribution of advection, okay, over conduction. Okay. Conduction, as I said, convection has a contribution from conduction as well as from advection. Okay. So if this number is greater than 1, okay, so if it is equal to 1, then there is no contribution of advection. Okay. So the heat transported from the wall to some distance, okay, let us say some L. Okay. In fact, I should not maybe use L here, let me use some H, okay, just to give you a non-dimensional physical representation of this non-dimensional number. So it tells you if you have a fluid element, vertical distance of H from the flat plate, okay, so you are calculating what is the contribution of both advection and conduction over conduction. Okay. If that value is equal to 1, so it means that all of this is happening only by conduction. Okay. And if it is greater than 1, you know that there is advection which is helping in the transport of heat. Okay. So therefore you are looking at, when you are looking at convection, you are looking at Nusselt numbers greater than 1, where you know that higher the value of Nusselt number, better is the heat transfer rate augmentation due to convection. Alright. So these are some of the non-dimensional numbers. Of course we have also come across Béjart number in the last class when we were looking at the entropy generation. Okay. So do you remember how we defined the Béjart number? In fact, I have also given one problem in your assignment to calculate the irreversibilities due to viscous dissipation, and yeah. Okay, so this is your you can say your entropy generation due to conduction heat transfer by entropy generation due to conduction plus viscous dissipation. Okay, so you can substitute the appropriate terms and you will arrive at what we have derived in the last class. So essentially it tells you, characterizes, quantifies okay, the entropy generation contributed by conduction over the total entropy generated. Okay, so this is a very useful number. Okay, so far entropy generation people have been talking about qualitatively, but now you can calculate the actual values from conduction, from viscous dissipation, that is the friction of the fluid which is generating entropy, and you can actually calculate the contribution of each, and then you can take the ratio and that gives you the Béjart number. So these are some of the non-dimensional numbers. I think more or less if you know these non-dimensional numbers, these will keep coming through the rest of the course. Okay, so I think most of the non-dimensional numbers are covered. You won't need anything apart from these numbers. Okay, can you think of any other non-dimensional numbers in heat transfer? Convective heat, related to convective heat transfer, for example. Huh? Okay, so the Stanton number, again it is an extension of the way that you are defining Nusselt number. Okay, it's simply ratio of Nusselt number to the Peclet number. Okay, sometimes the Reynolds number times Prandtl number is also referred to as the Peclet number. Alright, so this is nothing but your rho infinity u infinity L by what? Alpha. Okay, so this is also referred to as the Peclet number. Alright, so most of the times you have this pair coming into any of your expressions, so therefore they have combined that and it's denoted as a Peclet number. So any other non-dimensional numbers? Rayleigh numbers. Okay, so Rayleigh number again is basically nothing but your Grashof number times your Prandtl number. Okay, so these are the basic non-dimensional numbers. You can of course group them together and again give a different name to that. Okay, so far as single phase convective heat transfer is concerned, these are the ones. If you go to multi-phase heat transfer, say boiling or so on, then you will have other non-dimensional numbers. Bond number, Eötvös number, okay, capillary number, okay, and Weber number, so on and so forth, depending on the forces that you encounter. Okay, so any questions on this? Richardson number is again, as I said, if you group your Grashof number by Re square and you group them together as another non-dimensional number, that is called as the Richardson number. Okay. K disappeared. This is so this is HL by K. So K should cancel. I think it's straightforward, right? Your K cancels. If you already here from H, if you divide it by K directly cancels. Okay. So now what we will do next is to we will use the non-dimensional form. From here we will go one step forward. As I said, we will approximate the Navier-Stokes equations to much simpler set of equations for which we can find analytical solution. Okay, so that we will do for this particular boundary layer problem. Okay, so we will look at what we call as boundary layer approximation to the Navier-Stokes equations. Okay. So the reference figure which we will be using is still the same, whatever I have drawn here. We will be taking any boundary layer flow. For simplistic reason, you can assume that the free stream velocity does not vary with the axial location, but it could also vary. Still the boundary layer approximations are valid. Okay, so you have a momentum boundary layer, you have a thermal boundary layer, both simultaneously occurring due to a heat transfer which is taking place. We will start with the non-dimensional form of 2D incompressible steady state Navier-Stokes equation, and from here we will apply the scaling analysis. Okay, so when you want to reduce this full equation, you want to neglect some terms, so for that we have to understand the order of magnitude of each of these terms, you know, so there has to be a particular way that you are doing it. So this is done by the order of magnitude analysis. So the order of magnitude can be decided only if you scale the equations. Okay, so you should know to what extents the dimensions can go, for example, okay, and what extents the velocity can go. So once you know that, once you know the scale, so that gives you the order of magnitude of each term, from which you can neglect some terms for this particular problem. Okay, so the order of magnitude is basically decided through scaling. So let us introduce some order of magnitude of certain quantities here. So before that we will introduce what is called as a non-dimensional boundary layer thickness for velocity. Let us call this delta over bar, which is nothing but your delta by L. And obviously for the boundary layer flows, this quantity should be what? Very small. Okay, so this is where the scaling starts. Okay, so very first approximation that you introduce in the scaling is when you scale your boundary layer to the length of the plate, obviously this is very small quantity. Okay, so we will use this as the starting point and we will find the order of magnitude of other terms. Also when you look at the u velocity, that is the non-dimensional u velocity, what should be the approximate order of the magnitude? That should be approximately what? Very small. So what is the maximum value till which it can go? 1, right? So the order of magnitude should be approximately that. Okay, you look at the maximum value and you know what is the order of magnitude of that particular quantity. Okay, now we don't know whether V could be neglected, whether V is of the order of 1 or whether V could be neglected, so that we will have to decide now. Okay, so we will first write down the, okay, so your U goes to the order of 1, what about your capital X? Order of 1. Okay, now I am going to scale my Y non-dimensionally. So what I am going to do in the boundary layer, I am looking at X which is varying from 0 to all the way till the length L, and as far as the Y coordinate is concerned, I am mostly concerned within the confines of the boundary layer. Okay, the assumption here is that the boundary layer is the region of interest because the viscous effects are very important here. Outside the boundary layer you can treat this as an inviscid potential flow. Alright, so you do not have to solve the full Navier-Stokes equation. So therefore I will confine my domain to the extent of the boundary layer. So my, in that case my Y extent should be of the order of delta, yes. So this should be of the order of delta bar, which is of course much lesser than 1. Alright. Okay, so I will start with the terms one by one. Now you can tell me what will be the order of magnitude of du dx. So u is of the order of magnitude of 1, x is of the order of magnitude of 1. Okay, so this will be of the order of magnitude 1. Now how about d square u by dx square? That is nothing but d by dx of du by dx. So already this is of order of magnitude 1 divided by 1. So this should also be order of magnitude 1. Okay. So similarly we will do that in all the directions. So you have du dy. So u is of the order of magnitude 1, y is of the order of magnitude of delta. Okay. So therefore this will be order of magnitude of 1 over delta. Okay. Similarly, your d square u by dy square will be order of magnitude of 1 by delta square. So now we will have to decide what is the order of magnitude of the v velocity. Okay, so that we cannot directly hypothesize. So we have to use the continuity equation. Okay. So we can say my dv by dy, okay, is of the order of magnitude of du by dx, correct? So this should be exactly minus of this, right? So I know my dv by dx is of the order of magnitude of 1 and my v is of the order of magnitude delta. Therefore, yeah, this is u, right? So therefore v should be of the order of magnitude delta. Okay, so when I use delta here, it is the non-dimensional delta, so you can put an over bar because all these are non-dimensional variables. Dou u by dou y. Yes, we'll coming to that. Okay, we will come. So first we just write down and then we'll later say which order of magnitude is higher, which of the terms are probably more important than the other terms. So therefore we know, so your dv by dx now should be what? What should be the order of magnitude? And your d square v by dx square, again delta, so d square v by dy square delta by delta square 1 by, okay, so you have all the derivatives. Okay, so we will just substitute into the equations 1 by 1 and you know the order of magnitude. Okay, so let us start with the continuity here. So this will be of the order of magnitude 1 by 1, right? This is of the order of magnitude, what is the order of magnitude of v? Delta by delta, so both are of order of magnitude 1. Okay, so of course because you have only two terms and the two terms should balance each other, right? So they are both of the same order of magnitude. So coming to this term, use u into du by dx, so u is of the order of 1 by 1. Now here this is of the order of delta by delta, we don't know the order of magnitude of this, okay, but you can quickly see that the order of magnitude of these two are same, which is of the order of magnitude 1. Therefore in order to balance, this should be of the order of magnitude. Okay, now coming to this d square u by dx square, this is of the order of magnitude 1 upon 1 plus this is 1 upon delta square. Okay, now therefore if you compare these two terms, since your delta is very small, naturally this term has to be much more significant than this term, right? So you can say that you can neglect this term directly. Okay, so therefore if you neglect that term, so what should be the order of magnitude of Reynolds number such that all the terms have now the same order of magnitude? Delta square 1 over delta square. Okay, so therefore from here your Reynolds number should be of the order of magnitude 1 over delta what, square or delta? So what does it mean? So now this puts a constraint on the Reynolds number. So my delta is much lesser than 1, so therefore my Reynolds number should be, so only for this particular case this approximation is valid. So whenever I look at boundary layer flows, I am looking at very high Reynolds numbers. Okay. So now coming to this second, the y momentum equation. So what is the order of this? Delta by 1, and this delta square by delta. Okay. So now, so this you can see is of the order delta and delta, therefore this should be of the order delta. Coming to these two terms, you have this is delta by 1 plus you have delta by delta square. So this is 1 over delta, this is delta. Okay, so which is a more dominant term? 1 over delta. So which we can this neglect, and we already know the Reynolds number should be of the order of 1 over delta square. If you put that, you will find that now all the terms are of the order of delta. Okay, so all the terms in the y momentum equation are very small. Already your delta is very small, right? So therefore you can safely say that you can neglect all the terms without making much difference. Alright, if you are operating at high Reynolds number, all the y momentum terms are extremely small order of magnitude. Therefore, what comes out of this particular analysis, the order of magnitude analysis, is that, so number 1, your d square u by dy square is much greater than what? Right? This is the first coming from the x momentum equation, that is the first term that you neglected. Second, what it also means, your Reynolds number should be quite high, okay, greater than 1. And number 3, okay, all terms in v momentum are negligible. So what is the particular implication of this particular statement is that you can safely say that my dp by dy is of the order delta, so therefore the gradient is very small along the y direction, okay, or in other words my pressure is approximately constant along y. Okay, so this is a outcome of this particular statement number 3. So this has actually saved a lot of my computational effort. Okay, so what it is going to do is that I can safely say, if I take any x location, for example, so this states that the pressure here has to be the same pressure here, same here, same here. Okay, so what this means, I can calculate the pressure at this point based on inviscid flow analysis, and I can use the same pressure even inside the boundary layer. Okay, so if you apply the Navier-Stokes equation to outside the boundary layer, what will be the, so what will be the Navier-Stokes equation when you apply to the so if you look at the momentum equation, do you have any v momentum equation outside? No, so we are assuming the flow is in the x direction. So now the x momentum equation, you have only the u velocity, v velocity is not there, so this term is 0. Okay, and how about your viscous effects? Okay, so it's negligible, and therefore you have only two terms. One is your inertia term, u infinity du infinity by dx. Of course your u is nothing but u infinity outside. Okay, so that should be equal to minus dp by dx. Rho square, see all of this are nothing but your viscous effects. Okay, so if your viscous effects are negligible, outside in the free stream, so therefore you can safely neglect all of these. Alright. So now based on this we can calculate dou p infinity, yeah, because in this case it does not matter, p infinity and your p here, they are going to be the same. So you do not want to differentiate your free stream pressure from the pressure inside the boundary layer. Okay. Okay, so if you say that you do not have any pressure gradient, or in the other words you do not have any velocity variation, that is for flat plate flows that we are looking now, you can safely say my dp by dx is what? Zero, because my velocity, free stream velocity is not going to vary. Okay, so for cases where your free stream velocity varies, so if your free stream velocity is a function of x, you can have two kinds of flows. One, if you have adverse pressure gradient, so in this case your dp by dx should be, the pressure should keep increasing. Okay, so this should be greater than 0, therefore your velocity will keep decreasing. Okay, so that is the outcome. You can have favorable pressure gradient where your dp by dx should be less than 0, so that means your velocity keeps increasing. Okay, so you can have either of these depending on the kind of flow externally that you are looking at. If u infinity is equal to a constant, okay, then this is the best approximation, it is going to knock off the pressure term completely. Otherwise you have to consider either of these cases. So therefore so that is the approximation to the momentum equations. Coming to the energy equations, okay, so what will be the order of magnitude of theta? What do you think is the order of magnitude of theta? 1, right, you are scaling it between your wall temperature and the free stream temperature, so it has to be of the order of magnitude 1. So therefore this should be of the order of magnitude 1 by 1, and how about your V here? This should be delta, theta is already of the order of magnitude 1, so V is of the order of delta by, now when we are considering the temperature gradient, okay, which boundary layer we have to look at? Thermal boundary layer. So for temperature gradients in the thermal boundary layer, our Y scales with delta T, that so therefore we have to use this as the scaling parameter. Okay, so we will say that this goes as delta T bar. Alright, so coming to this term right here, so this is of the order of 1 by, this is of the order of 1 plus 1 by what? Delta T square. Okay, I do not have space, I am just squeezing in, and coming to this term right here, the order of magnitude of phi star, this is nothing but your I can write this as 2 times du by dx the whole square plus dv by dy the whole square plus dv by dx plus du by dy. I can divide it by half, I can multiply by half the whole square. So this is my viscous dissipation terms, and viscous dissipation terms, now if you look at it, this is of the order of 1 divided by 1, this is of the order of delta divided by delta, this is of the order delta by 1, and this is 1 by delta. So all this the whole square basically, right, they are all inside. So now which are the terms that we can neglect? Okay, so first coming to these two terms, between these two terms which is the smaller term? This is of the order of 1 over delta square. Okay, so this is going to be larger than, okay, so this can be neglected. Coming to the viscous dissipation term here, so this is of the order of 1, this is of the order of 1. Okay, now this is of the order of delta square, this is of the order of 1 over delta square. So this is the most significant term. So all of the terms can be safely neglected. So finally, if you write for temperature, you end up with the following equation, which is u d theta by dx plus v d theta by dy will be equal to 1 by Re PR into square plus your Eckert by Reynolds number times your 2. So 2 by 2 cancels there. You have what is the only term that is important? Du by dy the whole square. Okay, so now what should be the order of REPR? Okay, REPR, so this is of the order of magnitude of 1 over delta t square, right? So for all the terms to balance, REPR should be of the order of magnitude 1 over del t square, correct? Understood? So already you know Re is of the order of 1 over del square, therefore PR should be the order of del by delta t the whole square, or in other words your delta t by delta should be of the order of Prandtl number power minus half. Okay, so this is a very important conclusion. So this is the relationship between the ratio of your thermal boundary layer thickness to momentum boundary layer thickness with the Prandtl number. Okay, and what should be the order of magnitude of Eckert number by Reynolds number? So if you look at this term, this is again 1 over delta t square, right? This should be just one small thing. When you are looking at velocity gradient, you look at the momentum boundary layer thickness, right? When you look at the temperature gradients, you look at the thermal boundary. So this should be of the order of delta square, not delta t square. Okay. So now Eckert number by Reynolds number, what should be the order for all the terms to be equal? Is it delta square? Delta square, everyone agree? Okay. So we already know Reynolds number is 1 over delta square, therefore the order of Eckert number should be 1. Okay, so this finally will give you the boundary layer equations, which I am going to summarize and stop here. So after all these approximations, this is the final set of terms that you are going to retain. So your x momentum of course for a flat plate you can also have you won't have this term, but for favorable and adverse pressure gradients you can have dp dx, and your energy equation okay. So these are called the boundary layer equations. Okay, so any questions? I think I had been a little fast in the end, but I think you can fill up the, I think we did almost, you have to just go and revise, okay, how we have introduced the order of magnitude and we have skipped all the terms. The important conclusion now, you have a direct relationship between the ratio of your thermal and the momentum boundary layer thickness to the Prandtl number, and of course you have the order of magnitude of Reynolds number and the Eckert numbers. Alright. This point, okay, so this is coming directly from the y momentum equation, right? So this is correct. So what directly tells you is that your P should be invariant along y. Okay, so therefore if you calculate your pressure somewhere outside the boundary layer using the Euler equations, okay, the same pressure will be valid even inside the boundary layer. Okay, so we will stop here.